Good morning students. Today we will be discussing about the minimization of the Boolean expression. We are very pretty clear about the Boolean expression. So let us consider a Boolean expression that is f is equal to, that is in terms of a, b and c, and I am representing the Boolean expression f to be a dot b dot c plus a bar dot b dot c bar plus a dot b bar dot c. This is the Boolean expression which is basically in the canonical SOP form. Why I am telling this to be in the canonical SOP form? Because these are the individual min terms. I am having three min terms. This is the first min term, this is the second min term, and this is the third min term, and these min terms or the product terms are summed up. That is why it is in the standard SOP form. So to design this Boolean expression in form of the logic gates, I required the number of AND gates required is 3, as I am having 3 product terms, and the number of OR gate required is 1. So I will be designing the basic logic diagram to represent this Boolean function. So the number of AND, let us assume that the true form and the complemented form is readily available. Let me write down the expression for f again. It is a dot b dot c plus a bar dot b dot c bar plus a dot b bar dot c. So if I will be having the true form and the complemented form totally available in the situation, then I will be using 3 NAND gates and 1 OR gate to represent this Boolean function. Let me draw the logic circuit to represent this Boolean function. The first AND gate will be comprising of the variables a, b and c. The second AND gate will be comprising of a bar, b and c bar, and the third AND gate will be comprising of a, b bar and c. As these product terms are summed up, I will be requiring one OR gate to get the value of f. So I will be connecting all the AND gates to an OR gate, and I will be getting the output to be f. So for this representation, I required 3 AND gates and 1 OR gate to represent the Boolean function that is given above. So why we need minimization actually? We required minimization Why we required the minimization of Boolean function? We required the minimization of Boolean function in order to reduce the number of logic gates number of logic gates for implementation. So the less space will be required if you are reducing the number of the logic gates. So I will be minimizing the Boolean function, that was f is equal to a dot b dot c plus a bar dot b dot c bar plus a dot b bar dot c. I will be minimizing this Boolean expression in order to minimize the number of logic gates that is used. Thereby I can minimize the space for implementing this Boolean function. So from the first term and the third term I will be taking AC to be common, and I will be left with B here and B complement here. So I will be writing B plus B complement, and this term I will be writing as it is, that is a bar dot b dot c bar. And from the logic of the Boolean expression I am pretty clear that b plus b bar is always 1. That is why this value will be 1. So I will be getting AC plus a bar dot b dot c bar. Now I am having two product terms or two mean terms. So I will be using two AND gates and one OR gate for the implementation of this function. So let us know how to implement this function. I got the value of f to be AC plus a bar dot b dot c bar. This is the reduced or the minimized Boolean expression which I was getting previously. So I will be using two AND gates. As I am having two product terms here, then the number of AND gates I will be using will be 2, and the number of OR gates I will be using is 1. So I can represent this Boolean function in terms of the logic gates by drawing this circuit logic diagram. The first AND gate will be comprising of the value A and C. The second gate will be comprising of three variables, that is A bar, B and C bar, and the output from each of the AND gate I will be connecting it to an OR gate to get the output to be F. And here I have reduced the number of gates, that is the work of minimization in digital. So again here the true form and the complemented form of the variables are readily available. So if I am getting the minimized expression, will definitely reduce the number of logic gates and the space for implementation got the minimized expression that definitely reduced the number of logic gates, again the space for implementation, but it is not sure whether the expression we got is truly or not. We have reduced the number of guests by minimizing, but by minimization we are not at all confirmed that whether the expression we got is the ultimate minimized expression or not. So there comes the concept of K-map. Here comes the concept of K-map. So in minimizing the Boolean expression, we are not confirmed whether the expression we are getting is the minimum or not. Thereby K-map is introduced, and let me tell you what is K-map. K-map is the graphical representation. K-map is the graphical representation of the simplified Boolean expression. This K-map is called as Karnaugh map. It is the representation of the simplified version of the Boolean expression, and by representing the Boolean expression in the K-map, we are sure that the expression we are getting is the minimal among all. So let me tell you how the K-map is created. The K-map is created by cells in such a way that the adjacent cells will differ. The adjacent cells will differ by a single bit. Basically, the K-map is based on the gray code representation, in which we will be designing or constructing the number of cells, and the number of cells will be close to each other will be differing by a single bit. So in the K-map we will be learning about first the construction of K-map. Secondly, we will be learning about the mapping in K-map. And thirdly, we will be discussing about the minimization of Boolean expression based on K-map. So in the K-map we are having three steps. First one is we will be discussing about the construction, how the K-map is constructed. After that we will be pairing the group of ones and mapping will be done in the K-map. Lastly, we will be minimizing the Boolean expression by using K-map. So let me continue with the construction of K-map. important thing you have to learn about is the number of variables. If you are having a n variables, if the number of variables in the Boolean expression is n, then the number of cells in the K-map is equal to 2 to the power n. This is the most important thing you must know about the K-map. If I am having n to be 2, then my number of cells, if my n is 2, then my number of cells in the K-map is 4. If my n is equal to 3, the number of cells is equal to 8. So this is the important thing you have to learn about. In a n variable Boolean expression, you have to design or construct the K-map in which you will be having 2 to the power n number of cells. So first we will be discuss about the construction of two variable K-map. I have already told that the number of variables is n, then the number of cells will be 2 to the power n. So I am having the n to be 2 here, so my number of cells will be 2 to the power 2, that is 4. So first I will be drawing, let us consider my variables to be, let the variables to be A and B. So I will be having 4 number of cells. This is my 4 cells as my number of variables is 2, and my variable, one variable I am having is A and the other is B. I will be taking in the form of gray code representation. So this will be 0, this will be 1, this will be 0 and this will be 1. In this line of B, 0 will be denoted as the B complement and 1 to be B. Similarly, in the line of A, I will be having this to be A complement and this will be A. So, I will be having the main terms that will be M0 here. This will be my M1, this will be my M2 and this will be my M3. So, I will be representing the value of K-map in the mapping as A bar and this is your B bar. So, I will be having A bar into B bar here. In this cell, I will be having A bar into B. Here I will be having A into B bar and in the fourth cell I will be having AB. So my M0 is A bar B bar, M1 is A bar B, M2 is A B bar and M3 is AB. So this is how we will be constructing the K-map in case of 2 variables A and B. So now let us learn about the construction of K-map. With 3 variables. Let us know the number of cells when the n variable is 3. If n will be 3, then the number of cells will be 2 to the power 3, that will be equal to 8. I will be having 8 number of cells, having the 3 variables to be A, B and C. So to construct the 3 3 variable K-map, I will first draw 8 cells. This is my variable A, and I will be having B and C together here. This will be my A bar. This is A. This will be B bar into C bar. B bar C. This will be my BC, and this will be B into C bar. To represent the mean terms in the cells, I will denote this one to be M0. This will be my M1. From left to right, I will be writing M0 and M1. Again, I will be writing from right towards the left. So this will be M2 and this is M3. Similarly, it goes for this column also. So I will be having M4, M5 from the left to right, and from the right to left I will be having M6 and M7. To know about the mean terms here, I will be multiplying the A bar with this to get M0. So this will be A bar, B bar, C bar. For M1 it will be A bar, B bar, C. M3 it will be A bar into BC. M2 will be A bar, B, C bar. And in this column I will be multiplying A with this term. I will get A, B bar, C bar, A, B bar, C, A, B, C, A, B, C bar. So this is my main terms I will be getting, and this is how we are constructing the 2 variable K-map and the 3 variable K-map. So let us know about the mapping in the K-map. The second point is mapping in K-map. How the K-map is mapped in order to get the minimized Boolean function? Let us know the steps that are used for mapping is the first step that is used is make the groups of 1, make the group of ones in the group of 2, 4, 8, etc. First locate the min terms. Wherever you are getting the min terms, represent that to be 1. And in 1 you will make the pair of groups in the form of 2, 4 and 8. After that, try to pair the adjacent ones. Try to pair the adjacent ones in minimum number of groups. Then you will be pairing the adjacent one in the minimum number of groups. You can use the lowest number of groups as possible. And the third step is overlapping does not affect the pairing. In case the ones you are making the group will be overlapped to each other, that doesn't make any sense. Overlapping is also considered necessary. And the last step is make the individual groups in case take the individual group in case they do not pair with each other. In case someone will not get paired with each other, take that one to be a single group. Individually you can pair that one to be group. This is how you are mapping in the K-map. After mapping, you will be getting the minimized expression by writing the expression of the main terms of the Boolean function. Thank you everyone.